Well, first of all, thank you for inviting me. I'm really glad to be back in Lumini. It's always a lovely place to be at. And today I want to talk about a problem that I have been interested for a long time. That is, in essence, elimination of imaginaries in Henselian valued fields. And what I want to give today is sort of a very nice picture that we have gained so far for the equicharacteristic zero case. And this is joint work with Sylvain. So let me just fix a little bit my notation. Oh wait. Okay, so I'm going to always denote my Henselian valid field as K, right? And well, as usual, there are two particular sets that we're interested at looking at. One is the evaluation ring that I'm going to be denoting as O, and the other one is the maximum ideal that I'm going to be denoting as M. And I'm going to call the value group, the order Boolean group that I have there, usually denoted as gamma, and the quotient that I obtain by the evaluation ring by the maximal ideal, I'm going to be denoting as little k, that is just the residue field. So, well, before I actually start to give the picture of what we have gained so far for the elimination of imaginaries in Henselian valid fields of equicharacteristic zero, I would like to start with the history of it and mentioning where everything started. So this is a theorem that was proved by Haskell, Grushovsky, and McPherson, and it's a very nice theorem, and they clarified entirely the picture for ACVF, right? So what they did is they showed that ACVF eliminates imaginaries once you add the geometric sorts. So what do we do? For each natural number n, we add the sorts Sn, which in essence are adding all the codes for the sublattices of k to the n, right? So those are the three models of k to the n in generators. And for each possible lattice that you have, I'm going to denote as red S the reduction of S modulo n, right? This is just this quotient. You take your lattice and you quotient by the submodel of m times S. So I'm going to call as Cn the collection of all these reductions, right, when you vary your S over Sn. And the geometric sorts are, in essence, just the sort of the main field, the collection of all the codes for the lattices, and then the collection of all the Tn sorts. And there was a lot of hard work that continued from there, right? I'm just going to mention some of the results that were obtained afterwards, that all of them are very nice, according to myself. So to mention sort of them, well, there was the Petit case, that is a result of Grushovsky, Martin, and Ridho-Kikuchi. The separably closed case of valued fields of finite imperfection degree, that is a result of Hills, Kamensky, and Ridho-Kikuchi, and the real closed valued field case, that is a result by Miller. So all these are particular instances of Henselian valid fields that are unramified. And the question that we want to address is if somehow we could, like encompass all these results as a major principle or instances of a major principle. So let me just recall a theorem that pretty much all of us know, I guess. So whenever one is doing mole theory of Henselian valid fields, there is a spine philosophy, right? That is the also known Ax-Kochen Ershov principle. And what it tells you is that if you have a Henselian valid field that is unramified, then the first order theory of the Henselian valid field is completely determined by the first order theory of the residue field as a field, and the first order theory of the value group as an order Boolean group. And there is a principle that follows from this theorem that is, in essence, any possible method to question that you have about the Henselian valid field, you can reduce it into a question about the residue field and a question about the value group. And as far as I have heard, right, there was a conjecture that was formulated by Grushovsky in the 2000 that was the following question. That is, well, is there maybe an imaginary Ax-Kochen Ershov principle for Henselian valid fields that will be encompassing all the previous results that I mentioned before? And that's the question that we're trying to answer. And a year ago, we got two results independently that were looking into two orthogonal directions, right? So if we think about a Henselian valid field as a structure that is combining the complexity of the residue field and the value group, you could try to make this question a little bit more tame by trying to make one of them very, very tame and try to understand which are the troubles that the other part of the structure brings to the picture of elimination of imaginaries in Hensel invalid fields. So the first approach is the Hills-Riddoch-Kikuchi approach. So what they do is they sort of try to make the value group very, very tame, in particular definably complete. That includes only two theories of order Boolean groups, that is divisible order Boolean groups, or groups that are elementary equivalent to the integers, so models of Pressburg arithmetic. And they understand the problems that the residue field brings to the picture. And there is the other approach, that is what I did in part of my PhD thesis, that is, we want to make the residue field as tame as possible, so in particular I assume it to be algebraically closed, and I understood which were the troubles that the complexity of the value group brings to the picture of elimination of imaginaries in Hensel invalid fields. So I want to present the results that we obtain in each of these two, and what this talk is about is, in essence, how we, Sylvain and myself, combine these two things to provide a nice result for the equicharacteristic zero case. So let's get back to the Hills-Riddoch-Kikuchi approach. So what is the context? I'm going to have a Hensel invalid field of equicharacteristic zero, and I'm going to assume that the value group is either divisible or a C group. And now they want to make the residue field hard, like an arbitrary field of a characteristic zero. So it's not longer going to be algebraically closed, and the question that they were addressing is, which are the new sorts that are required in order to eliminate imaginaries once you make the residue field a little bit more wild. And here's my spoiler. So what they came up with is what they call the K-linear sorts. So that's what I'm going to introduce. So let's say that you start with a lattice of rank n in k to the n, right? So I'm changing a little bit here in my notation. I'm going to look at the lattice, the reduction of the lattice modulo maximal ideal. And I'm denoting it now to be BS, right? Because, well, it is well known that this structure carries a vector space structure over the residue field, right? This is just a vector space over the residue field. So now what we want to do is we want to consider the two-sorted structure, right? Where in one side I have the residue field, and in the other one I have the reduction of S by the maximal ideal. So I'm going to introduce the language of vector spaces, right? Where we're going to have two sorts. And in the first sort, I'm going to have a sort for the field that I'm going to equip with the language of rings. And in the second sort, I'm going to have a sort for the vector space V, right, that I'm going to equip with the language of groups. So I'm going to have the zero and then the addition. And then I'm going to have a map that goes from the Cartesian product of the residue field and the vector space into the vector space that we're going to interpret as usual scalar multiplication. So now we're going to be working in the theory of dimension n vector spaces over a field. And for each possible interpretable set that I have over the vector space sort, so here I have my X and my vector space V in this language, I'm going to do the following. So pick up your favorite lattice of rank n, right? And I'm going to denote like this, X hat of these two structure. In essence, the interpretation of this set in the structure that I obtain where I take in the first side the residue field, and in the other side the vector space that is obtained by taking the reduction of the lattice by the maximal ideal. So I'm going to call Tnx, in essence, the collection of all these interpretations when I vary my lattice over Sn. So let's give some examples of these Tnx sorts. So for instance, if you start with your set just the entire vector space, what you obtain is the usual Tn sorts, right? But if you look at the one element quotient of the vector space, so we are collapsing the entire vector space into just one single point, you obtain something that is just isomorphic to Sn. So here is what they call the K-linear imaginaries. So what you're going to do for this part is, in essence, you're going to take the collection of all these Tnx sorts, right, where you range over all the natural numbers and all the possible interpretable sets that you might have. Good? So far? So the theorem that Martin and Silvan proof was the following, and I'm giving a simplified version. That is, in essence, let's say that you start with a Hensel invalid field of equicharacteristic 0, and you assume the value group to be definably complete. Again, this is including only two theories that are those that are divisible or C groups. And they assume that the residue field eliminates the existing finity quantifier. So what they obtain is that the entire Hensel invalid field is going to have weak elimination of imaginaries down to the geometric sorts, classical geometric sorts from ACVF, the linear sorts into the residue field, and the entire EQ extension of the value group. So there are two remarks I want to do about this result. The first one is that there is a little bit of redundancy, right? Because for instance, here, as I mentioned, we have some copies of SN, and they also appear here, but I think for pedagogical purposes, it's nicer, this presentation. And the second remark I want to do is, well, they actually prove a lot in that paper. This is a very, very nice paper. So they also give a complete picture for the mixed unramified characteristic 0 mixed case unramified. And they also prove elimination of imaginaries for BFA down to geometric sorts. So I'm just giving a simplified version. And now I want to start talking about the second approach that we have. That was my approach. So let's get back to which is the context. So for instance, let's say that you have a Hensel invalid field of equicharacteristic 0. And now I'm going to do the opposite. I'm going to make my residue field to be very, very easy. So in particular, I'm going to assume that it's algebraically closed. And now I want to make the value group much more general, so it's not longer going to be divisible or a C group. And the question that I was addressing back then is, well, which are the new sorts that are required in order to have elimination of imaginaries once we make the value group more general? And what I introduce is what I call the stabilizer sorts. So let me just say a few things. Yes?
So more general is any gamma group, or do you have a specific?
I work with a finite spine case. I'll get there. So, I mean, everything that you need to add is just codes for models. But to actually give a nice presentation of the language, we need to work in the finite spine case. So okay, let me just give you the setting. So what will mean to actually have a little bit more of complexity for order-Belin groups, right? So if you look at those that are definably complete, they have a very nice property that they share. That is, for instance, there are no definable convex groups in these two theories. But something that will be easy is just, like going to the class of polyregular groups. Those only have finitely many convex groups. So for instance, an example will be taking just the direct sum of the integers with itself with the lexicographic order. So here I have my picture, right? And this one has a convex group that is in essence just looking at those elements such that the first coordinate is 0, right? So what is the issue that arises once you allow the presence of more convex definable subgroups? That is, in essence, you're going to have more definable in segments. And by that, maybe what do I mean? Like when you work in Q, well, I don't know, can people see here?
Yeah. Maybe you use the other one and raise it.
Okay, so there. So when we work here, well, this is a minimal, and then it's not hard to prove that definable in segments always look like arrays of these four, right? Just intervals closed by some element alpha, right? So here, the thing is, not all the n segments are going to look like these two things. So for instance, once you allow the presence of this convex definable subgroup, right, you can also define this n segment that I highlighted in yellow that is in essence looking at those elements in the order-Belin group that the first coordinate is going to be bigger or equal than 1, right? So it's those such that the quotient is strictly bigger than the zero set, right? So we're going to have more definable in segments. And I guess this is going to answer your question. So the next step is what will be, like the real setting where we're going to be working with. So there is a very nice class of order Boolean groups that I prefer to use the terminology of bounded regular rank because it really sticks to the nature of the convex definable subgroups, but I'm not going to really define what the rank is because it's a definition that is rather technical and I feel like not very illustrative for the talk, but in the literature, they also appear as those that have finite spines, right? So this is a class of order Boolean groups in which you're going to have or allow the presence of countably many definable convex subgroups, but you do not allow uniform definable families of convex subgroups, right? So how is the picture of general order Boolean groups that we obtain? So here in this little corner, we have those that are very nice, that are those that are definable complete, that are Presburger arithmetic or divisible order Boolean groups. A little bit beyond, you have those that are DP minimal, right? That by a result of Francie, Pierre, and Eric are precisely those such that the quotient of gamma by n times gamma is always finite, and that, for instance, has the example that I pointed out. A little bit beyond, you have those that are strongly dependent, that by a result of Halevi and Hasson, are contained in those that are of bounded regular rank. So this is fairly a large class of order Boolean groups. Stuff that you're not allowing there is, for instance, order Boolean groups, this order Boolean group, right, where you take the infinite direct sum of the integers with itself, countably many copies. And the issue with this one is you have a uniform definable family of convex groups. So I'm not allowing that, but it's large enough. And what I want to say is that in this setting, where you have a Henselian valid field whose value group has bounded regular rank, and the residue field is algebraically closed, everything that you need in order to have elimination of imaginaries is in essence adding codes for all the definable submodels m of k to the n. So if you believe that, the real question is, well, which are the new submodels that appear once you make the value group with bounded regular rank? And just for pedagogical purposes, right, let's try to understand what happens in the one-dimensional case. So this is just using a folklore result, right, that tells you that there is a one-to-one correspondence between the submodels of k and the n-segments of gamma, right? So here's my picture. So you have your n-segment, and here's your model, right? So how do you go back and forth? Well, if you have your model, in essence, the corresponding segment is just taking the valuation of the elements that are in your model and going backwards. Well, if you have your n-segment, how do you get back your model? Well, you take the elements in the field whose valuation is lying in that n-segment. And when you look at these, you say, well, that looks a lot like a ball, right? But yes, in fact, it's a ball, and we call it generalized balls. But the main issue is now you're going to have new definable n-segments, like the one that I highlighted here. So you don't have radius, but rather they look, like cones that are in there. And the higher dimensional case is not so hard to prove, right? That whenever you look at a model that is in k to the n, then the model is going to be definably isomorphic to a direct sum of one-dimensional models. These are just copies of the main field, or in essence, fractional ideals of the evaluation ring. And I'm not going to give precisely the presentation of the language that you need. Everything that I'm going to say is that, in essence, everything that you need to do, or like a way in order to add codes for these models, is you can think about it as quotients of the upper triangular matrices by some stabilizers. So let's denote B and K, in essence, the group of upper triangular invertible n times n matrices. And for a finite sequence of one-dimensional models, I'm going to associate a canonical model, C1, Cn, that is in essence the one that you obtain for this sequence, let's say 1 until en, just look at the model, or I guess I denote it to be C1 to Cn. Cn is the one that you obtain by taking the standard basis. Right? And yes, yes, yes. And this is my standard basis of Kn. Yes. So I'm allowing the coefficients to range over these one-dimensional models. So those are just linear combinations where the coefficient is. Yeah. Yeah. So okay, there is this canonical. Don't worry, like there is one canonical model that you can associate to that, and then you might look at some subgroup of the upper triangular matrices that is in essence the stabilizer of that standard one. So what you take is just a subgroup of linear transformations that don't move that canonical model, and then what I call the stabilizer sorts are in essence the main field, and then these quotients. And the nice representation is that you can actually find this family to be complete, but I'm not going to go into detail through that. So the result that we obtained before is, well, in essence, if you have a Henselian-Wallet field of equicharacteristic 0, and you assume that the residue field is algebraically closed, and the value group has bounded regular rank, then the Henselian-Wallet field is going to have weak elimination of imaginaries down to the stabilizer sorts and the EQ expansion of the value group. So with a little bit more of work, you can actually show full elimination of imaginaries whenever you assume the value group to be DP minimal. But I don't want to go into details through that. And here's where we're combining forces, right? So the question is, well, how further we could put together these results that we had. This is a theorem that I proved with Sylvain. So if you look at a Henselian-Wallet field of equicharacteristic 0, and we assume that the value group has bounded regular rank, and you look at the theory of this Henselian-Wallet field, if you want, in the standard language, where you add a relation for the divisibility, we have the following two results. So whenever the value group is DP minimal, that means when you look at the quotients of gamma by n times gamma, that is always finite, then the theory is going to have weak elimination of imaginaries down to the stabilizer sorts that I introduced, the linear sorts that Martin and Sylvain introduced, and the EQ expansion of the value group. And alternatively, you could just drop the condition on the value group to be DP minimal, and what we obtain is if you add angular components, then the theory has weak elimination of imaginaries down to the stabilizer sorts, the linear sorts of the residue field, and the EQ expansion of gamma. Well, it's just making your exact sequence to split, right? So you just had a map that allows you to split that sequence, right? The invertible of the residue field, and then RV, and then gamma. Okay? Oh, shit. Okay. So I want to mention a theorem that I think is very nice also in the history of elimination of imaginaries, though it's not the theorem that we used, but as far as I understand, it was proved by Grishowski, and it was used by Will Johnson to give a very, very much simplified proof of elimination of imaginaries for ACVF. So what the criterion says is that whenever you have a first-order theory with home sort K, right, and you have a collection of sorts that you distinguish, let's name it G, if you have the following two conditions that I call density of definable types or coding of definable types, then the theory has weak elimination of imaginaries down to the distinguished sorts that you have. So what is density of definable types? In essence, is telling you that always that you look at a one-definable set of the home sort, you're able to find a type that is centering that set, and that is going to be definable over the algebraic closure of the code of that set. And coding of definable types is telling you Well, if you look at a definable type in your home sort, right, and you look at the canonical base of that type, the canonical base is going to be interdefinable with a tuple of elements in your distinguished sorts. That is going to be possibly infinite. So the thing is, this theorem is the one that I used to prove the previous result. The issue is density of definable types will collapse when you look at the more general setting. So there is no chance, like for instance, if you make the residue field, like to be horrible, like Q, everything is going to fail. So no chance to have density of definable types. And what is going to be the strategy now? Well, we want to sort of work or to extend, right, to a nicer structure, right? So what we're going to do is, I here have my Hensel-invalid field, K, right, my gamma and my residue field. And what I'm going to do is to go to the maximal unramified extension, right? So the value group is staying equal, and the residue field is going to be algebraically closed. And there is no criterion, let's say, that we could state in an abstract way for the principle that we are using to have elimination of imaginaries, but broadly speaking, the strategy follows in two steps, right, that in essence work for Hensel-invalid fields. That now what we're going to do is to look for density of definable types in a reduct, right? And then the second step is looking for completions of this type that are invariant extensions that are going to be invariant, but invariant over a very large set. So let me just formalize what I just said. So let's recall what our context is. So let's say that you have a Hensel-invalid field, K, of equicharacteristic 0, and I'm always going to use the subscript 1 to refer to the maximal unramified extension. And we're going to be working in two different languages. So the first one is L1, that is the one that I'm usually used for the maximal unramified extension. That is, we're going to have a two-sorted language, and in one of the sorts we have the main field, and in the second one we have the value group with the map with evaluation, and we take gamma Morleyized, while I'm going to call L the language that we use for the Hensel-invalid field, that is the three-sorted language, where we put in one of the sorts the main field, the second one RV, and the third one gamma Morleyized. And generally, just to remark, I'm always using the subscript 1 whenever I refer to the language L1 for one types, algebraic closure, or space of types, and so on. Well, you add predicates for the definable sets. Or is it stably embedded gamma? Or? Gamma is always stably embedded in the equicharacteristic 0 case. So, okay. So, okay, what is step 1? Like, what we're going to have is, let's say that we have a Hensel-invalid field of equicharacteristic 0, and we're assuming the value group to have bounded regular rank. And you look at a set that is algebraically closed in EQ, right? And you pick up your favorite definable subset in K to the n, right? The one that you prefer, that I have highlighted here in light blue. That's your favorite one. And then what we, right? Well, I'm trying to make my graphical representation. And what we're able to do is, I'm going to be able to give you a type in the reduct of L1, right, that satisfies the following two conditions. The type is going to be consistent with this definable set, right, and is going to be definable, or, well, the canonical base can be computed in the trace of A over the stabilizer sorts and the EQ expansion of the value group. Those are the two conditions that I'm going to record. And let me maybe give you some sketch of how the argument goes for this. So for the one-dimensional case, we're going to pick up our favorite set that is going to be L-definable. And the proof goes in two steps. So the first one is we're going to find a generalizable U, definable in the reduct over A, such that the generic type is going to be consistent with X. And by generic here, we take what you expect. We take the type that says X is going to lie in the generalized ball and is not going to belong to any other proper generalizable. And the second step is, in essence, completing this type to a full type in the language L1 that I don't want to go into details of that part, but in essence, whenever the ball that you're considering is closed, that is going to have one unique extension. And when it's open, everything that you need to do is to make choices for cosets that you have for certain subgroups, right? That in essence, this is just the convex group delta plus n times gamma. That will be it. So actually, yes?
X is not definable in L1, right?
Yes. No, that's a key point.
So what do you mean by P of little x union capital X is consistent?
Well, all of this, the thing can see, like the model can see, right? Like K can see like the reduct of that one. You're working in the smaller insular bullet field, right? So this is a type. It's a partial type.
So are you working in the pair? I mean, X might not have the same meaning in K and in K and the right side.
Yes, and there are some technical things. So always that you have somehow like this reduct, we have shown that there is a unique extension to the maximal unramified one. So at the end, it's going to be the same, but I'm trying to really slow it and keep it.
Sorry.
Really putting all the technical part on the carpet, but there is no issue.
It's just that I didn't understand.
So yes, there is a unique extension and it all works, okay? So, yeah, so I don't know how much time do I have left?
You have about half an hour, 28 minutes.
20 minutes? Yeah, maybe I'm going a little bit fast. I have been doing my best to speak the lowest possible that I can. But as you might see, I'm working on that, yeah.
Would you like us to ask more questions?
You can ask more questions.
It's okay.
You can pull everything out of the carpet if you want.
Well, maybe I'm going to, it's just I really want to get to the last part, that is, it becomes clear where step 1 and step 2 are useful. So maybe what I will do is I'm going to skip some details on how you will do step 1. And if I have time, I'll get back to this. Because I think I had too many slides. So, okay, so in essence, how do you actually generalize this notion for the higher dimensional case, right? And the idea is, what we're going to do is to fiber, right? And follow by induction. And this is, in essence, following an idea that was present already in Grishowski's criterion, or the proof, where it's clear, right, that once you assume density of definable types for one definable sets, right, you actually obtain density of definable types for n-definable sets, right? And this is going to be technical, but in essence, like what we're doing is, well, you now pick up your favorite set, right, X in n variables, right? And you want to proceed by induction. So what you're going to do is to take your set, and you're going to take the projection of that set into the first coordinate. That is going to give you this set here, right? That is a one-definable set, right? By the one-dimensional case, you can find a type that is entering that set that is consistent with this set, right? And you might like to take a realization of that type. And then what you do is, in essence, you want to look at the fiber and then apply induction to find a type that is definable too, right? And then you would like to take the type of the tuple AB. So what I describe is, in essence, the generalized idea, but it has very technical work, let's say, in actually trying to make that work by transitivity. And in essence, what we do is we study this issue by looking at the potential difference that we might have between both algebraic closures, and then use the fact that the upper triangular matrices are a solvable group to study these two things into just one-dimensional sets. So maybe I gave you a broad sketch on how one finds the definable type that is consistent, right, with the set. And the coding of definable types is a nice idea, but I'm also like sketching it broadly. and is in essence somehow present in the argument that Will Johnson provide for the proof of elimination of imaginaries in ACVF, but that you can generalize actually in a resplendent way, right? Even adding structure over gamma. So what is going to be the principle? So always that you want to code definable types, right? In this reduct, the problem of coding definable types translates into coding the following information, that is coding definable subspaces of k to the n. That is always an easy problem. The second one is coding valued vector space structure, right, over k vector spaces. And that is where you need to do something. And then some additional data, right, in the value group. That is the reason for which we're going through the entire EQ, and EQ takes care of this matter. But in essence, what you need to do is always that you want to code or a valued vector structure on k to the n. In essence, this is always completely determined by the closed balls that contain the zero vector, right? The entire topology is just determined by that, and these closed balls are in essence just also models of k to the n, and that's why you need to add those. The tricky part was, in fact, showing that you have separated bases and that you can do all this in a definable way over A. So now I want to start moving through the second step, that is, how do we actually build invariant extensions? So let's get back to the setting. Let's say that you have a lattice of rank n, right, in k to the n. And remember that we always have an associated vector space that is obtained over the residual field, that is obtained by taking the quotient of the lattice by the maximal ideal, right? And I'm going to define lin A, right, the collection of all these vector spaces that we obtain whenever we vary over those lattices that are definable over A in the sense of ACVF, if you want, or L1. So here's my graphical representation. I have my S and sorts, right? And some points inside there are going to be definable over A. And for each lattice, I'm looking at the vector space that I associate and I put it on top. And lin A is all this structure that I have here. Okay? And A is going to be fixed. That's important. So in particular, this is stably embedded. But so how do we go, in essence, from a definable type in this reduct to a full type, right, in the entire language? So the theorem that we got is, in essence, the following. So let's say that you have M and N models of the theory, and it's an elementary extension of M, and both are sufficiently saturated and homogeneous. And you look at an algebraically closed set, A, that is contained in M. And now you're going to take an element in the field part, in N, right? And if you assume that the type in the reduct in L1 is invariant under the action of this group, the group of automorphisms of M that fix A, then the full type of A over M is going to be invariant, but over a larger set. So it's going to be invariant under the action of this group, that is the group of automorphisms of the entire structure, over A, the trace of M over RV, and the trace of M over lin A. And you might be complaining, right, that this set is very, very big, right, and it's as big as the model. And yes, you can, I mean, it's going to be very big, but it's good enough, and the reason is because it's going to be stably embedded, right? And I'm going to highlight one result, right, that shows you that why these structures are nice, right? So for instance, this is a result of Martin and Sylvain. So if you work in a sufficiently saturated and homogeneous structure, and you look at a multi-sorted structure, D, that is stably embedded, and you pick up an element E in M, so if it is always the case that this element is fixed by the group of automorphisms of the entire structure and the trace of M over this stably embedded set D, then this imaginary already belongs to the definable closure of that set, right? So in our context, this set is in essence the entire RV and Lin A. So now I want to go through the weekly coding, right? That is sort of the entire point. So what is the idea? Always that you have a Hessian valid field of equicharacteristic 0 whose value group has bounded regular rank. If you pick up an imaginary element in EQ, and now we're going to look at the algebraic closure of that element that I'm going to name as A, then this imaginary is going to belong to the definable closure of all this set. So what is this? G prime A is in essence the trace of A over the stabilizer sorts and the EQ expansion of the value group. And the second part is in essence looking at the trace of A of the EQ expansion of RV and Lin over G prime of A. Okay, so once you have this, you can see why we have these two hypotheses, right? So in essence, what we're trying to do later, or is what we're now thinking, is how to break imaginaries in RV, right? So if you have an angular component, well, you can think about RV in essence as just a product of the residue field and the value group, right? And the condition over the value group being dp minimal is just citing a result that was already in the paper of Martin and Sylvain, that is somehow whenever you have the value group that is dp minimal, then you can break imaginaries in RV down to the linear imaginary sorts and gamma EQ. So how do we actually do this? So let's prove this theorem. That is the easiest proof. So let's say that you work in a model that is sufficiently saturated and homogeneous, and you look at an imaginary element, right? And you look at A, the algebraic closure of this imaginary element, right? Now, since you have an imaginary element, well, you know that it's going to be the projection of some equivalence class, right? So in particular, there is a definable map G, right, and a tuple in the main field sort, such that whenever you applied the function to that tuple, you get back your imaginary, right? So now I'm going to look at X, the preimage of that imaginary under the function G, right? And what you have obtained is in essence a definable set in variables over the main field, right? So now you're going to apply the first step, right? So the first step is in essence allowing you to find a type in the reduct that is going to be consistent with X, and that is going to, its canonical base lies over the trace of A of the stabilizer sorts and the EQ expansion of the value group. And what happens? Always that you take a realization of this partial type, well, this realization is going to lie in X, and is going to be a realization of P. So in particular, the type over the reduct is going to be definable over the trace of the A of the geometric sorts and the EQ expansion of A of the value group. And now you can apply the second step, right? That was telling you that always that you have a type in the reduct that was invariant over the action of the group of automorphisms of M, that is now fixing G prime of A. It will guarantee that the full type is now invariant over a larger set. So what we have here, well, is if you take a realization of this type, the type in the reduct is definable over this trace, right? In particular, it's going to be invariant over the action of the group of the automorphism of M fixing this set. So you can apply step 2, and that tells you that the full type now is going to be invariant over all this very large set, right? So this, again, is just the trace of A over the stabilizer sorts and the EQ expansion of gamma. And this other part is simply just the trace of M over RV and the Lin sorts over G prime of A, right? So what is going to happen? Well, in particular, you have that this imaginary is in the definable closure of this element. So since the type is invariant, right? Any automorphism of this group that is fixing all this large set is going to also fix this point. So by the fact that I highlighted, and the fact that this set D, that is RV and lin of G prime A, is stably embedded, you can conclude that in particular, this element belongs to the definable closure of all this set. And now you have that this imaginary is in the definable closure of all this set, right? So what does that mean? In particular, you have that there is a definable function over the trace of the stabilizer sorts and gamma IQ of A. And you have some tuple, right, that lies over RVM and the linear part of G prime of A, such that that imaginary is equal to H of C, right? So now what I want to do is I want to take the preimage of that imaginary that I'm going to call as C, right? And now what you have obtained is a definable set over A, right, that is now contained over this set. So C is going to be contained in the union of RB and lin of G prime of A. So the code of this set is in particular going to lie in the EQ expansion of the trace of A, right, of this set, RV, and the linear part of G prime of A, and, oh, well, that was the end of this proof. I was about to finish, I guess. Oh, great. Well, we're almost done. All this part, I mean, like, everything was, until here is actually the technical part, right? But now what we have, right, is you have this set. The code is already in what we want. And now this particular imaginary, well, we have shown that belongs to the definable closure of the trace of A over the stabilizer sorts and the EQ expansion of gamma. And the code of C, right? Because always that you have a point in C, you can compute this imaginary. So this is in particular an element that lies in the trace of A of the EQ expansion, right? Of RV and lin G prime A, and this G prime A, that is just the trace of A over the geometric sorts and the EQ expansion of A. So thank you very much for your attention. I don't know if...
Okay, so thanks a lot. That's very nice. Are there more questions? Yes.
Thank you. I had two comments to make. First of all, I wanted to correct the record slightly. It's very flattering to say that it all started with the work.
Yeah, Holly. I should have mentioned Holly, yes.
Well, I wanted to mention the results on one variable elimination of imaginaries by Jan Hawley in the case of real closed and algebraically closed valued fields.
I'm worried.
And Philip Scowcroft on in the Piatics. And this really amazing result, which I don't know whether people know about anymore, of McIntyre and Scowcroft, where they showed that if you take the Piatics and add a couple of function symbols, which is very precise, then the question of whether or not you have elimination of imaginaries in the Piatics is independent of the continuum hypothesis. And that always seemed to be like this amazing kind of statement. Okay, so my other question was, do the new sorts that you've identified add anything in the case of, say, of ACVF? I mean, are they just the old ones?
Well, what happens, for instance, for the linear sorts, I mean, is a result of Grushovsky, right? That for the... Okay, let me get back, because we have two sorts. Right, so for the case of the linear sorts of Sylvan, right, we know that in essence all of those are coded in, right, these ones. So you have here the essence; those are the classical classes things for the lattices, and there is a hidden result here, right, that that is in a paper of Uri, that whenever you look at two linear structures, that is just, like looking at the family of all the possible vector spaces that you have over the reductions of the S by the maximal ideal when your residue field is algebraically closed. That structure has elimination of imaginaries. So not really. I mean, like all of them are going to be interdefinable over there, right? So for the real closed case, Silvana also proved it. But for my sorts, were them here, I mean, technically, I'm adding a little bit more, right? Because I for instance, never mentioned the TN sorts. So here I'm looking at models that are allowing, for instance, M and O, right? The maximal ideal M and O in all these possible models, right? So what happens is that all the TN sorts, right, because there are torsors, they're interdefinable with a model of higher dimension. So, I mean, up to interdefinability, right? But, I mean, as you prove, the result is optimal.
Well, yes, yeah. we don't need them in the classic case. So in that sense, of course, they're not adding anything new. But I guess what I was really thinking of is having identified these linear sorts, whether that's going to help with the problem of eliminating imaginaries when you add restricted analytic functions.
Yeah, that I'm not so sure. Like,
no. Okay.
Yeah.
So why don't you take that? Thank you.
I had a question about this slide. Does it matter if you take the upper triangular matrices or all matrices? Like, would you get the same sort?
No,
or
well,
is it important to do the upper?
It's the same. Like, if
okay.
you're just planning to add codes for the models, right? The thing is, for our proof, like we were discussing with Sivan, like the real title of our paper should be like Elimination of Imaginary Solvability Induction. So what is happening, like, and we use a lot, like is this canonical result that whenever you have the upper triangular matrices, this is a solvable group, right? So you can use this trick of looking the code of the model and making it interdefinable with unary sets. Right? And that's why I want to express it as upper triangular matrices.
Okay.
Are there other questions? Okay, so I have one. So you've restricted to the case of the finite spines.
Yes.
And I know it's harder if you don't, but is it impossible?
No. But, I mean, the real notion that you need over the value group that will make this proof to work is density of definable types over the value group. And the unique case that we have proved that to go, like to have density of definable types over the reduct is for the finite spine case. So for the more general case, we don't have a proof yet, right? But what will need to happen, right, is that you will add codes for all the possible models, but then you need to parameterize for all the possible one-dimensional ones, right? And then since you have uniform definable families of convex groups, well, you're going to also have intersections of all of them, so the language is not so nice. I think it's going to be possible, but I'm not so. I mean, we haven't sorted out. Like, so far, the proof complete is for this case. Does that clarify the question?
It does.
Yes.
Okay, so that's it. Let's thank Mariana again. Oh, did you want to say something, Sylvain?
Just that I don't think the linear sorts were invented by me and Martin. They were invented by Udi when he tried to give a precise statement of the possible Ax-Kochen Ershov imaginary statement. They're in your preprint already.
How much is?
Yeah. Well, preprint is maybe a big word. Anyway, so they're not Martin and mine. They're also they go back further.
Yeah, well, I apologize for that, and Holly and...
No.
Yeah.
But about the solvable, I think it's very important there also. I mean, when you have just general linear imaginaries with GLN acting on them, you don't have any kind of elimination of imaginaries for them. But if they have flags, which means you restrict the subgroup to solvable groups, then you can describe the imaginary.
Ah, okay.
Maybe it doesn't matter what you said because you're just reducing two linear imaginaries, but then what somebody to understand the linear imaginaries, they're really different if they have these definable flags.
Okay. Yeah. Okay. No. Well, I'll think. I think longer on it. Like, yeah, I'll think longer on it. Yeah, I guess, like, you mean for whenever the residual field is algebraically close, but it's you always have this flatness. So, maybe can we talk later? Yeah. So,
You always have flags. Always have flags.
Yes.
For the S-model, of course, for the linear sorts, also some with an A, you always have flags.
In the I mean, for valid field. For Hessian valid field, you always have flags.
I know. I'm just. It was not a question. It was not a mathematical question. It was just a question of whether the flags are important, right? And whether.
Oh, I see.
That's at least that's what I understood.
Okay.
Okay then. So let's. Let's thank Mariana again.